Greetings everybody. So today we are going to discuss about the one shot of a new chapter, which is rotational motion. First, we are previously known about the linear motion. What is linear motion? Linear motion is a motion which occurs in a single dimension. In a single dimension there's a linear motion, but again it varies on the type of motion it is. If it is a projectile motion, that would be a 2D motion. Now linear motion or translation motion is the one which occurs only in a single direction. Now here angular motion or circular motion or uniform circular motion are good examples of what type of motion. These are examples of 2D motions. 2D motion. So rotational motion, circular motion are examples of 2D motion. And here we are going to discuss about the quantities. As we have linear quantities for linear motion, we do have angular quantities for angular motions, which are going to be discussed in this class. So here angular quantities are those which describe the angular characteristics of angular motion. Now among that, first characteristic which we are going to discuss over here is angular displacement. Let's suppose we have um, you know let's suppose we have a particle. Let's suppose we are having a particle which is bound at this point, which particle known as P, which is bound at the point P to the center of the circle, which is O, by a distance which is represented by R, or we can also call it as a radius. Now when when the particle subtends an angle theta, when the particle subtends an angle theta which has the radius of the particle, which has the radius in which, let's suppose we have the particle which subtends an angle theta which has the arc length formed by the arc of that angle theta equal to the radius of that circle. At that moment, we say that S is equals to R, due to which an angle is formed between S and R, which is known as theta, and that angle is equal to 57.3 degree. 57.3 degree, and that angle which is 57.3 degree is known as radian. RAD, radian. Now what is the mathematical derivation of it? When it comes to its mathematical derivation, first let us discuss what is it. It is basically an angle which is subtended by when the particle in a circular path moves towards the circle, making an angle theta. Whenever the particle is revolving in an angular motion and subtends an angle theta, it is known as angular displacement. So this angular displacement is represented in terms of three major quantities. In SI system, we measure it in radian. In British engineering system, we measure it in degree, while in other systems such as another unit for it is revolution. First, let us discuss how did the above explanation come out. So we know that the circumference of a circle, S can be represented as a circumference. It can be represented as arc length, because here we were representing the arc length, a part of the circumference, and now we are going to represent the circumference of the circle. Circumference of the circle is represented by 2 pi r. 2 pi r. As we know that it is having formula S is equals to theta r. Actually, the formula S is equals to theta r is also derived on the basis of the value of pi. What is pi in actual? Pi is, as we previously discussed in a previous video, it is a ratio of circumference to diameter. And that ratio of circumference to diameter has a constant value which is 22 upon 7, or 3.14. Now, when we calculate the value of pi in terms of degree, then in terms of degree, pi is equals to pi is equals to 180 degree. And if we are supposed to calculate the value of 2 pi indicates 360 degree, right? 2 pi indicates 360 degree. Now when we are supposed to multiply 360 with radius, the total degrees of the circle with the radius, we'll get our answer, which is 2 pi r as the circumference of the circle. This is how the formula is calculated. Now coming to another part where we calculated the value of S is equals to theta r. We know that S is equals to theta r. On the basis of that same formula, we are supposed to calculate 2 pi. 2 pi is equals to how many degrees? 360 degree, or we can represent 360 degree by theta, and theta is equals to S upon r. Again, that would be a long definition derivation. We are just going for the one shot, and here, since both equations are equal, 2 pi r radian. Actually, this is a value which is given in terms of radian, because radian is represented in the terms of pi. 2 pi r is equals to theta r, right? R and r will be cancelled out, due to which it will, sorry, there's another value, radian. Its unit is necessary, because we are going to find the unit, that how radian is equal to 57.3 degree. 2 pi radian. So here radian will be equal to 360 degree. Now here we know that theta upon 2 pi, and we know that theta upon 2 pi is equals to 360 upon 2 pi, because theta is equals to 360, due to which when we are going to calculate it, we'll have our answer 57.3 degree. It's a rounded off value, approximate value, so the actual answer will be given in the calculator. So this is how we find the value of theta, find the value of radian. Now 1 radian is equals to 57.3 degree, 1 degree is equals to 0.0174 radian, 0.0174 radian, 0.0174 radian. Likewise, if we talk about 1 radian is equals to how many revolution, 1 radian is equals to 1 radian is equals to how many revolution. First, let us understand what is a revolution. When a circle completes one complete angle of 360, then it is known as one revolution. We can say that one revolution is equals to 360 degree. One revolution is equals to 360 degree. Likewise, in order to find 1 degree, we can divide one revolution 1 upon 360, due to which whatever the answer would be, that would be equal to revolution. 1 degree is equals to that much amount of revolution. Apart from that, if we talk about radian, one revolution is equals to how many radians? One revolution is equals to 2 pi radian. Why is it considered as 2 pi radian? Because we know that one revolution is equals to 360 degree, and 360 degree is equals to 2 pi radian. One revolution is equals to 2 pi radian. Likewise, one radian is equals to 1 upon 2 pi. So this is how we calculated. These are some basic points. One more thing, that radian is a dimensionless quantity. It does not has any dimension, and yes, this is not having any sort of dimension. Now coming to some points which I wanted to discuss over here. And consider a motion of a single particle of mass m in a single radius r. Suppose this motion is taking place by attaching the particle p and the end of a massless rigid rod of length r, whose other end is pivoted at the center o at the circular path as shown in figure 5.1a. As the particle is moving on the circular path, the rod OP rotates in the plane of the circle. As previously told, the axis of rotation passes through the pivot O and is normal to the plane of rotation. Consider a system of axis as shown in figure 5.1. The z-axis is taken along the axis of rotation with point O as the origin of coordinate. Axes x and y are taken in the plane of rotation while OP is rotating. Suppose at any instant t its position is OP1, making theta with x-axis. At later time its position will be t plus delta t, which means change in time, plus t. Let its position be op2, making an angle theta plus delta theta. So at that moment the angle which would be subtended would be in terms of angular displacement, which is a dimensionless quantity. What is the unit? No unit. It is dimensionless. It is having no unit. uh, yes, in SI system we have its supplementary unit, which is known as the radian. In SI system, there is a supplementary unit, radian. It is a dimensionless quantity. Angle delta theta defines the angular displacement of OP during the time interval delta t. For very small value of delta theta, the angular displacement is a vector quantity. Moreover, there's another point I want to discuss here, that S is equals to theta r. This is an equation which is valid whenever we are utilizing the value of theta in radians, because it describes the value of radian, because theta is basically what it is, the ratio of arc length to radius, due to which it describes the value of radian. So this is the only condition which is valid in radian. Now of course, if angular displacement is counterclockwise, that would be considered as positive, as defined by right hand thumb rule as well, and if it is clockwise, then it would be negative. How we can also utilize right hand thumb rule to determine its direction. How, if we are supposed to place our hand as the position of R, then curl our fingers, that would be the position of the angular displacement. And at that moment, when we are going to turn our thumb uh, erect erected, that erection of our tongue, uh, that erection of our thumb will cause us to give the direction of angular displacement, which is along the axis of rotation. Now, if OP is rotating, the point P covers a distance s is equals to 2 pi r in one revolution of P. One revolution is equals to 360 degree, and all such things are given. Now, likewise, we are going to discuss another terminology over here, which is in terms of, these are some important MCQs point as well. Value of pi upon 3, pi upon 3 is equals to how many degrees, and pi upon 2 is equals to how many degrees, what is value of 2 pi, what is value of 4 pi, what is value of 9 pi upon 6, and these are some important MCQs point. Now coming forward, some next point, which is angular velocity. Angular velocity is basically, as we are having the rate of change of linear displacement as linear velocity, rate of change of angular displacement is known as angular velocity. Here it can be defined as theta upon t, theta upon t. So it is expressed basically in 3 units: degree per second, radian per second, and revolution per second. Sometimes also in revolution per minute. The commercial unit we are utilizing in cars, in speedometers in cars, is a revolution per minute. So this is how we do it. But the SI unit which we are going to say for it is radian per second. This is theta upon t. Theta upon t only represents in degree per second, but if we are supposed to calculate it in radian per second, then it would be 2 pi upon t, because we know that theta is equals to 360 and 360 is equals to 2 pi. Now this is not enough for calculating the angular velocity, as we are having the average linear velocity, we are also having average angular velocity as well. How? See, as angular velocity as angular velocity as angular velocity is increased, see, as we are having angular velocities, angular velocity one hand side, if we consider about linear velocity, first and foremost, linear velocity uh, basically has an average velocity, average linear velocity, instantaneous velocity. At any instant, if the angular velocity is taken, then that velocity would be considered as delta theta upon delta t. Of course, there's a derivation for it, we are only going through the one shot. One more thing here, if you are supposed to apply instantaneous, then we need to apply limit, and limit will be applied on the increment of delta theta upon delta t. Limit theta approaches oops sorry t t0, t approaches to 0, right? So this is how we calculate the instantaneous velocity. For average velocity, we tend to calculate the delta theta upon delta t. Now average angular velocity is given by theta 1 minus theta naught t1 upon t1 minus t naught. Now when average velocity is equals to instantaneous velocity, it is known as uniform angular velocity. And same goes with acceleration. If we are going to calculate acceleration, that would be average angular acceleration and instantaneous angular acceleration. Same concepts go for angular acceleration as well. So this is how we actually do it. Moreover, coming to some important conversations here, as we know that the unit of angular velocity is radian per second. This is the correct formula for calculating uh, the value of angular velocity in radian per second. While if we talk about revolution per second, if we are supposed to talk about revolution per second, then it would be considered in terms of one revolution per 1 second. And sometimes we are also given a condition that how many that one revolution per minute is equals to how many radian per second. One revolution per minute is equals to how many radian per second. So at that moment, one revolution per minute is equals to 2 pi upon 60 radian per second, because we know that one revolution is equals to radian is equals to 2 pi radian, and 1 minute is equals to 60 second, due to which 2 pi upon 60 radian per second is the answer. Likewise, if we talk about some other conditions which are mentioned, uh, if we look a bit closely at the equation, we can see that 1 upon t represents frequency. So at that moment, we can say that omega, here it is represented by omega actually. So omega is equals to 2 pi f instead of 1 upon t. So this is the formula for angular frequency. One MCQ is that the dimension of angular velocity is same as angular frequency as well as frequency. Likewise, if we are supposed to calculate it, angular frequency, this is the formula of angular frequency: omega upon 2 pi. F is equals to omega upon 2 pi. Now coming to some book points. Uh, One more thing, let me just clear average acceleration as well. Acceleration is also the same. Rate of change of angular acceleration is non rate of change of angular velocity is on angular acceleration. Same concept go, which includes average angular acceleration, instantaneous average acceleration. Moreover, as we talk about uh, applying the concept of uniform and non-uniform angular acceleration, that will be equal if average and instantaneous angular acceleration are equal. This is known as uh, uniform angular acceleration, and not then non-uniform angular acceleration. So this is how we do it. Apart from that, if we talk about its unit is again, it is radian per second square. Radian per second square. Oops, it's a bit long. Radian per second square. We can also express it as degree per second square. Uh, but most conveniently we utilize it radian per second square. We can also utilize it as revolution per second square, but mostly we utilize it as radian per second square. So this is how we do it. One more thing that I would like to highlight over here is one more thing that I would like to highlight over here is about uh, its dimension. Dimension would be, of course, simple: t minus 2. And apart from that, angular acceleration, direction of angular acceleration is positive. If angular acceleration is positive, if the angular motion is in counterclockwise direction, because when the circle is moving in counterclockwise direction, that will be having angular acceleration moving outward the circle, due to which it would be positive. If it is moving clockwise, then that would be moving inward the circle, due to which it would be considered as negative. How we are also going to discuss the concept of radial acceleration after it. But for now, uh, here let us put the equation over here: 2 pi per t square, or in other words, we can conveniently put it as omega per t, right? Delta omega upon delta t. So what we are going to do here is to utilize the formula of omega. What is the value of omega? Omega is equals to 2 pi f. 2 pi f upon t. 2 pi f upon t. Now at that moment, 2 pi alpha, it is represented by alpha. So here alpha is equals to 2 pi f upon t. Angular acceleration is equals to 2 pi f upon t. Now in this moment, 2 pi f upon t basically here represents us the angular acceleration in terms of radial acceleration. Now radial acceleration is what we are going to discuss that as well. Now coming to the book point, here let us discuss a few things about the book as well. Instantaneous angular velocity is the limit of ratio delta theta upon delta t as delta t following instant t approaches to 0. In this limit, when delta t approaches 0, the angular displacement would be infinitely small, so it would be a vector quantity, and the angular velocity is defined by this. So angular velocity, angular displacement, angular acceleration are also vector quantities. When we switch on the fan, we notice that its angular velocity goes on increasing. We said that it has an angular acceleration. We define angular acceleration as the rate of change of angular velocity if theta I and theta f are the value of instantaneous velocity of a rotating body at instants ti and tf. The average angular acceleration during interval dr minus di is given by average angular acceleration is omega f up minus omega I. The instantaneous angular acceleration is the limit of ratio delta omega upon delta t as delta t approaches 0. Instantaneous angular acceleration is given by this. Angular acceleration is also a vector quantity whose magnitude is given by equation 5.5, whose direction is along the axis of rotation. Once more, again, angular acceleration, angular displacement, and angular velocity have the same direction. Unit is radian per second square. And this is the formula for radial acceleration. Apart from that, some relationship between angular and linear quantities. These are the linear equations of motion and angular equations of motion. So this is basically the simple relation. Just we are here to we can easily substitute the value of linear velocity or angular velocity, linear acceleration, and angular acceleration. Linear displacement is angular displacement. But a question arises that can we have a correlation using mathematical expression between linear and angular quantities? So the answer for this is yes. We can have a correlation. How? See, we know that value of s is equals to theta r. When an angle is substantiated, the value of s becomes theta r. Let me just see if I can find it as well. As we have previously studied, the value of s is equals to theta r. So in this case, uh, whenever, let's suppose we have a wheel. This is a wheel. This is at the center. It's the radius. Actually, it's a bit misdrawn. So when the wheel covers a distance, it subtends an angle theta, which would be considered as its angular displacement, But since it will subtend an angle theta, it will also have an tangential displacement, which means if the wheel is moving angularly, it will also have tangential displacement, and that tangential displacement would be the linear displacement occurring. Let's suppose if there's a wheel, that wheels covers 360 degree, covers a complete rotation, complete revolution, 360 degree, right? So once it covers a complete revolution of 360 degree, it must cover some sort of linear displacement as well. Linear displacement in term And that linear displacement is expressed in terms of tangential displacement, and that is given by this formula: s is equal to theta r, where s is the tangential distance and theta is the angular distance. So this is the relation. Now if we are supposed to divide it by t, divide both equations by t, s is equals to s upon t is equals to theta upon tr, right? So if you're supposed to divide both, now at that moment, dividing can not only cause to provide us that, but we need to actually there's a mistake. Sorry for that. Oops. So here s is equals to theta r, right? S is equals to theta r. Now here, first we are going to apply increment, because we are going to take the tangential distance and angular distance at a small interval of time. So applying increment, we're going to apply increment. Delta s is equals to delta theta r, right? Now once we apply increment, what we are going to do right now is to divide it by delta t. When you're going to divide it by delta t, it will become delta s upon delta t is equals to delta theta upon delta t into r. As a result, delta s upon delta t is equals to velocity, and delta theta upon delta t is equals to omega. Now here in this case, we are having two quantities, which is uh, v. Now here v will not be considered as a linear velocity, it will be the tangential velocity. because when tangential distance is covered, of course there would be rate of change of tangential distance, which would be tangential velocity. That tangential velocity basically is having the same direction as tangential displacement as well as tangential acceleration, and that would be perpendicular to the radius of the circle. Now, in other words, we can also say that angle between V, R and omega is equals to 90 degree. V, R and omega is equals to 90 degree. So this is how we do it. Apart from that, if we are supposed to calculate angular acceleration, same goes with angular acceleration. We are only going to apply the increment and divide it by delta t, due to which we'll get our formula, which is alpha, oops, a is equals to r alpha. Now at that moment, a is equals to r alpha will be the equation which would be gained. Now at that moment, if we talk about, oops, a is equals to r alpha, here as you can see, uh, a represents the tangential acceleration which is perpendicular to the radius of the circle, and alpha which is also perpendicular. So all of these are having the same angle, which is 90 degree. As we come to discuss about centripetal force and centripetal acceleration now. What is centripetal force? A force. First and foremost, it is important to discuss what is centripetal force. A force which is directed towards the center of the circle, or which tends to move the particle towards the center of the circle, in simple words is known as centripetal force. Or in other words, it is also known as a center seeking force. And that centripetal force, whenever it causes the particle to move in the central path, causes to have a centripetal acceleration, and that centripetal acceleration is given by the formula. Actually there's a long derivation for it as well, how centripetal acceleration is derived. uh, let's derive that as well. Let's suppose if we are having a particle, this is a particle, this particle is having its displacement in this direction. It is a linear, it is going in a linear particle, it is going in a linear motion, but due to the linear at centripetal force, it will tend to move in a circular path. So in other words, we can say that its velocity, due to because rate of change of displacement, here velocity will be considered in this direction on this part, while after an instant delta t, we can say that the velocity of the particle will be in this direction, and that would be considered as v1, that would be considered as v2. Now when we are going to take the addition, when you're going to add both of the vectors, this is the vector v1, this is vector v2, and this is what we call as the vector, oops, actually there's a mistake in it. So here, oops, there's a mistake actually. Let me just raise it. Just I was in a hurry, so it happens. So first vector, last vector, and this is the final vector delta v. So here this is v2, this is v1. Likewise, if we talk about the circular motion, when this is what we call as the linear motion, but since this linear motion was not occurred due to the centripetal force, and that centripetal force was caused due to the central particle here, the origin from where the centripetal force originized, and here that was originated from a distance r. This was the distance r, that was the distance r from both of each other, and the arc length which was between r and r was s, or we can also call it as delta s. So if we come to talk about both figures, r delta s, and v1 v2 and delta v, both are isosceles triangles, such that sides of delta s and r and delta v and v1 are equal. So we can say, according to isosceles triangle, we can just take the ratios of both, such that if we are having delta v, we can make it equal to delta v upon v is equals to, because we are considering v, because v2 and v1 both are isosceles triangles, part of isosceles triangles, so we are considering that as both same. Likewise, delta s upon r. Now when we are going to calculate it, this is the equation. So if we are going to manipulate it, delta V is equals to delta S into V upon R, because we are separating the increment on one hand side and other constants on the other side. So in this case, this is the equation. But now what we actually need to do is to divide both of the equations by delta T. Delta V upon delta T, delta V upon delta T is equals to delta S upon delta T into V upon R, such that when we are going to multiply it, we know that delta V upon delta T is equals to acceleration. That would be considered as centripetal acceleration, and that would be considered as velocity delta S upon delta T, which is velocity into velocity upon R, and centripetal acceleration over here is considered as V square upon R. This is how we calculate it. Now when we are going to further manipulate it, we can also convert it into R omega square by putting the value of V, which will be equal to R omega square. Now we can also further manipulate it. How? We can take value of omega is equals to 2 pi f whole square. It will be equal to 4 pi square f square r. This is what we call as the radial acceleration. Radial acceleration is having its formula as 4 pi square f square r. Now this is some mathematical derivation. Now again, you know the dimension of centripetal acceleration is direction. Its direction is towards the center of the circle. And one more thing I would like to highlight over here is about the centripetal acceleration as well as centripetal force. Centripetal force, whenever centripetal force is occurring, there will be a centripetal acceleration, and centripetal force is directed towards center of the circle. Now we know that according to second law of motion, F is equals to ma, and acceleration is having the formula, original formula, v square upon r. So putting the value of acceleration, mv square upon r is the final formula. Now we can further manipulate it by adding mr omega square, as well as we can also write it as m 4 pi square f square r, pi square f square r. So this is how we calculate it, right? So this is how we do it. After that, when it comes to some other concepts, moment of inertia is also simple. Basically, as we are having angular acceleration analogous to linear acceleration, we are having mass as a linear quantity analogous to moment of inertia. How? See, consider a mass m attached to the end of a massless rod as shown in figure 5.8. Let us assume that bearing at point O is frictionless. Let the system be in a horizontal plane. A force F is acting on the mass perpendicular to the rod. Then it will accelerate the mass according to F is equals to ma. In doing so, the force will cause the mass to rotate about O, since tangential acceleration is related to angular acceleration. So we can say that here tangential acceleration is equals to angular acceleration, which is equals to r alpha. Now, since it is equal to r alpha, we are gonna supposed to put value of r alpha. Now we know that we know that as turning effect is produced by torque, it would therefore be better to write the equation for rotation in terms of torque. Here, instead of writing mr alpha, we are supposed to multiply it by r on both sides. When we are going to multiply it on by r on both sides, we can get the formula, which is torque. Rf is equals to torque, cross product of position vector and force is equals to torque, while on the other hand side, mr square alpha, oops, what am I writing, mr square alpha is equals to torque, where we know that the value of mr square is equals to moment of inertia. Here torque is analogous to force, alpha is analogous to linear acceleration, and mr square is analogous to mass. Now in linear quantity, we know that quantity of matter is mass, but here the quantity of angular motion contained in a body is equals to angular momentum, and quantity of mass contained in an angular motion is known as moment of inertia. Here force is also known as moment of force, angular momentum is also known as moment of momentum, and moment of inertia, basically it is uh, part of it is basically known as it is derived from inertia. Inertia depends on mass, and moment of inertia depends on mass. It depends on mass as well as a perpendicular distance. Here r is not the radius, it is basically the perpendicular distance. It is a perpendicular distance which is squared perpendicular to the center of the circle. It is the distance which is squared perpendicular to the center of the circle. Apart from that, F is replaced by tau, A by alpha, M by mr square. The quantity is known as moment of inertia, which is represented by I, and that basically is not only dependent on mass but also dependent on r square. Apart from that, it is a vector quantity again, and some other factors which determine it includes the density of the body, because mass and density are directly proportional. After that, shape of the body can also determine it. Shape of the body, density of the body, size of the body, and distance from the axis of rotation. It is the distance from the axis of rotation. Basically, it is the squared distance which is perpendicular to the axis of rotation. Apart from that, this square distance which is perpendicular to the axis of rotation is known as r. Now, within different objects according to their geometry have different moment of inertia. And if radius is increased, moment of inertia is increased. And if mass is increased, moment of inertia is decreased. Apart from that, these are some common objects from which we are supposed to find the moment of inertia. As you can see, this is a thin rod. If there is a thin rod in which a mass particle is tied to the center of the circle from a distance L, from a distance L. So the distance which is between the center axis of rotation and mass is known as L upon 2, due to which we can put the value m L square, oops, let me just, it is equals to ml square upon 12 because here as we are going to take the value, it will be into 4. There's a mistake actually, it's not 12, it's 2, it's 2. There's a mistake. Moreover, thin ring or hoop. If there is a thin ring or hoop, then the outer and inner radius would be considered. If there is a thick ring or hoop, then outer and inner radius will be considered. That would be written as a square plus b square. But if not, that if this is a thin loop as given in this condition, that will be considered as simple mr square. Likewise, if there is a solid cylinder will have 1 upon 2 mr square. These are all based on their geometry, because solid cylinder basically is having its radius, and that radius basically is having the particle tied over here, and that particle is basically having a 1 upon 2, 1 upon 2, which means here uh, the since the solid disk is 3D shape, so we are going to add 1 upon 2 because it is having two sides of the mr square, because we are not going to calculate the general formula of mr square. This is only the general formula mr square. But in order to calculate the mass, in order to calculate the moment of inertia of several particles, because the uh, different areas, different particles, as you can see within all of these shapes, geometries, we are having different construction of the geometry, as well as we are having different distribution of masses. So if there's different distribution of masses, that different distribution of masses uh, needs to be summarized into m1 r1 square plus m2 r2 square plus m2 r3 square, m3 r3 square. So in this case we can write it as mn rn n minus 1 n is equals to n minus 1. So this is how we write it. Likewise, coming to the final point, which is 2 upon 5 mr square. This is for a sphere. Now coming to another concept, which is angular momentum over here. Angular momentum is what? Angular momentum is defined as the momentum which tends to keep the body within its angular motion is known as angular momentum, or quantity of angular motion is known as angular momentum, like as we are having the linear momentum. Apart from that, when it comes to some other concepts I wanted to clear over here, is that it is a vector quantity. It is basically having, it is represented by L, and it is a cross product of position vector and linear momentum. And as it is a cross product position vector and linear momentum, it is having its unit as kilogram meter into meter, because r is having meter, and kilogram meter per second into meter. It is equals to kilogram meter square per second, where kilogram meter square per second is the SI unit of angular momentum. The the dimension of angular momentum is same as Planck's constant. Planck's constant is also having uh, the unit as kilogram meter square per second, but it is also the unit of Planck's constant. But the SI unit of Planck's constant is joule second. Joule second is also the unit of angular momentum, but SI unit of angular momentum is kilogram meter square per second. Apart from that, what actually happens is that we are going to calculate it with a right hand thumb rule, that if we are having two quantities, r position vector and linear momentum, both of these are basically perpendicular to each other, and the angle which would be formed, sine theta, would be the angle formed between r and p. Moreover, if we are supposed to talk about angle between r, p and l, all of these are mutually perpendicular, such that one side is this, one side is this, one side is this. How? See, this is r, this is p, which is mutually perpendicular because it is on linear momentum is along the tangent, and r is along the radius of the circle, which means both of these are mutually perpendicular. But when it comes to the direction of angular momentum's direction is to along the axis of rotation, while linear momentum's direction is along the tangent of the circle, whereas angular momentum's direction is parallel to angular displacement, angular velocity and angular acceleration, and position vector's direction is um, same as centrifugal force. By the way, centrifugal force is something which is considered as a pseudo force, because it is in actual not a force, but it is a force which is created in a reaction to the centripetal force. As whenever a centripetal force is created by any sort of other force, so it causes to create a centrifugal force. Now, what is centripetal force here? Centripetal force here is itself not a quantity, right? It can be created by any force. Likewise, if we are having a stone which is tied by a string, and we are supposed to uh, rotate that stone, and by holding the string into a circular pathway, so at that moment the stone basically will not be having any sort of centripetal force to hold it. The tension which is causing the stone to tension in the string which is causing the stone to rotate in the circular pathway will be the centripetal force. So itself, centripetal force is nothing. It is basically a force which is dependent, which becomes something when we are rotating something in an angular motion. Likewise, if we are taking the revolution of earth and sun, earth when revolving around the sun is having the centripetal force. uh, there's no such centripetal force which is revolving the earth around the sun. The gravitational force of attraction of sun is greater than earth, as a result of which gravitational force of attraction of sun causes to attract the earth towards it, as a result of which it acts as a centripetal force to make the earth rotate in a circular pathway in a revolution. So this is how we do it. Apart from that, when it comes to some other questions, dimension is again simple: ml square t minus 1. Ml square t minus 1, same as Planck's constant. Planck's constant is the smallest constant. It is having its value as 6.634 into 10 to the power minus 34 joule second. It is smallest constant in physics. And we can also consider value of L as I omega. How? We are going to check the derivation as well. I guess this is all. Apart from that, how L is equals to I omega. There is something I wanted to discuss over here. L is equals to I omega. What does this mean? This means that here, if we are having the magnitude of P, P is having its magnitude as MVR. MVR. It will be now written as, now here we know that value of V is what? V is equals to R omega. V is equals to R omega into r m. Now when you're going to write the value, it will be equal to mr square omega. Mr square omega As a result of it, this will be formed. Now at that moment, mr square is equals to what? It is equals to moment of inertia, and omega is the original value. So I omega can also be written as the value of angular momentum. Law of conservation of angular momentum, what does it say? It is also known as Kepler's second law. This law says us that whenever there is an angular motion, that angular motion will have a value of angular momentum which would be conserved, which means the angular momentum of a body in an angular motion will remain constant unless there is a net external force acting on it. Now what is the net external force? Let's suppose a particle is there. Particle is rotating around a circular path, in a circular path, and at that moment, as it is rotating in a circular path, that particle will, rotate and continue its motion and remain in that angular motion momentum unless there is an external torque acting on it, which means as there is no external torque acting on it, the torque, if the angular momentum is conserved, torque would be zero. The derivation is given over here in such a manner that here, if we are having L is equals to RP, L is equals to RP. Now, when we are going to divide it by increment, first we are going to apply increment, and once when we are going to divide it by delta t, we'll have our answer as delta L upon delta uh, R into P upon delta t. Now, we know that there is a theorem in maths that if you are going to, multiply delta P and R, then here if we are supposed to write delta r into delta p into r plus delta r into p, that will give us the same result. This is a theorem in maths that if you are going to write, if we are going to write delta p into r plus delta r into p, both of these conditions when added will give us a constant result, a same result. So this would be considered as a theorem which we are going to utilize in this condition. So as a theorem will be utilized in this condition, after applying the theorem, r into delta p upon delta t plus p into delta r upon delta t. Now we know that delta p upon delta t is equals to what? Is equals to force. As we know that rate of change of linear momentum is what? It is force, and p is the value which is equals to mv. So delta r upon delta t is equals to v. So here when we are going to write all of these values, these values will be written as delta l upon delta t is equals to r into f plus 0. Now why is a 0 present over here? 0 is present over here because we know that value of p is mv. P is MV. M, I'm just writing a small x so that I can show you why it's being multiplied. It's a cross product. Now MV, and here on the other hand side, we are having the value of delta R upon delta T as V. So when V and V will be multiplied, both of these are vectors. When vectors are being multiplied, they and what when same vectors multiply, we know that v cross v, whenever same vectors multiply I cross I, then the angle between them is 0, due to which sine 0 will be equal to 0, and this entire value will be equal to 0, due to which when it will multiply with m, that will also be 0, due to which the final value which would be obtained is 0. So this would be the equation, and once it is done, the rest of the equation obtained will be the cross product of position vector and force. Cross product of position vector and force is equals to torque. At that moment, torque is the final answer. So we can say that rate of change of angular momentum is also equal to torque, right? And one more thing that I would like to highlight over here is that uh, as the net external torque applied on the system is equals to 0, net external torque applied on the system is equals to 0, net external torque applied on the system is equals to 0, then delta L, we are saying that no external torque is applied, which means torque is equals to 0. As torque is equals to 0, we can say that delta L upon delta T is equals to 0, which means the value of rate of change of angular momentum is 0, which means here that delta L remains, angular momentum remains conserved. After which when we are supposed to discuss about a few concepts about what is torque. Torque is basically moment of force. It is moment of force. What does that mean? Whenever a force is applied on an object perpendicular to the uh, at a perpendicular distance from that object, then at that moment that force which is applied at a perpendicular distance from the axis of rotation of that object to produce a turning effect of force is known as torque. Now torque, whenever we are utilizing our the door handle is always just like this is the door, this is the axis of rotation of door. I'm just making it a big a bit bigger. The handle or door knob is always you know uh, attached away from the door, is always attached away from the door at a distance r, at a distance r. I am calling it as r, and that distance r which is perpendicular to the axis of rotation of the door is known as moment arm, is known as moment arm. And greater the moment arm there is, greater will be the torque. Greater the force applied, greater will be the torque. We do not um create the door handle over this side of the door. We do not make the door handle or attach the door and door knob nearly extremely near towards the doorknob. That's not the case at all. This is now why, because less distance between, less perpendicular distance between the door knob and the axis of rotation will cause to have less amount of torque produced, due to which the person will tend to face difficulty while opening the door, even though if there's a handle over there, but the person will tend to feel a difficulty because he will not get the enough amount of turning effect of force in order to produce the torque. So torque about a point is equal to the force times the distance displacement. It's actually displacement measured perpendicular to the force, which is known as moment arm. Which is known as moment arm. This is what we call as moment arm and represented by R. And here torque is represented by Greek letter tau. And torque, when it comes to torque, we discuss about sign. So torque is positive. Torque is positive in first quadrant. Torque is positive in first quadrant, as well as it is positive in second quadrant. In third and fourth quadrant it is negative. In third and fourth quadrant it is negative. Why? Because sine theta is positive in first and second quadrant and negative in third and fourth quadrant. These are some common MCQs point, as well as um, torque is counterclockwise. If the torque is counterclockwise it is positive. If torque is and clockwise, then it is negative. If it is clockwise, then that would be in the third and fourth quadrant. If it is counterclockwise, that would be in first and second quadrant. This is how we classify a force, a torque. And if the torque is acting at an angle of 270 degree, if it is acting at an angle of 270 degree, then the torque considered would be negative. So this is a basic explanation. And unit of torque, Newton meter. SI unit is Newton meter. Also unit is joule. Also there's another unit of it which is known as joule. And in CGS we are having dyne meter, dyne centimeter, sorry, we are having dyne centimeter. Also erg, but not the CGS unit. Also erg, not erg. Also erg, but originally CGS is having its unit as dyne centimeter. Likewise in FPS, FPS is having feet, it is having feet into libra, foot into libra. So these are some common units. Apart from that, dimension is quite clear. ML is square T minus 2. We are known about it previously as well. So when not in balance, system rotates in direction of torque. So here, as you can see, there are some common examples. Here, torque is maximum. Torque is equals to F into L. It is maximum. Torque is equals to F into L. It is maximum. Torque is equals to F into L. It is maximum when um, the length, or it's not a length actually, we call it as the moment arm, because it is a perpendicular distance from the axis of rotation, due to which it will be maximum over here. In this case torque is 0 because the angle between the angle between the force and the torque applied is zero, due to which sine zero is equal to zero. After that, if we talk about other conditions include that equilibrium of torque. If we are having if the net torque applied on a system is not equal to zero, if the net torque applied on a system is not equal to zero, then the system will tend to rotate in the direction of higher torque. For suppose at the pivot is having more amount of torque on F1 side, less amount of torque on F2 side, due to which more amount of torque applied on F1 side will have higher torque produced on F1 side, due to which the pivot will rotate towards the side of F1 where there is a higher torque. It's a common observation when we are utilizing seesaw. In seesaw, when the person who is having, if there's an unbalanced seesaw, usually we are having a balanced seesaw. Why is that so? In order to maintain equilibrium, such that the only difference which can lead to produce torque will be the force. If there's an unbalanced seesaw which is having a, a larger and a smaller radius, actually it's a momentum, so we call it as momentum generally. So a larger and smaller momentum, so at that moment it will lead to unbalanced torque, and that will lead to unequilibrium, that will not be considered as equilibrium. So net torque applied is equals to zero, net torque applied is equals to zero in the equilibrium. Likewise, net force applied is equals to zero in equilibrium. If the seesaw is not having any force applied as well as not having any torque applied, net torque and net force applied is equals to zero, the seesaw is at equilibrium. These are the two conditions. Apart from which, when it comes to some common observations, when we come to discuss about rotational motion, we have orbital velocity. Orbital velocity, first and foremost, is important to understand what is orbital velocity. Orbital velocity is the velocity, first and foremost, whenever we launch a satellite. When we launch a satellite, we know that gravitational force of attraction of Earth tends to attract the satellite towards itself. So there's a specific type of velocity which is required to escape the gravitational field of Earth, and that velocity is known as escape velocity, which is 11,200 meter per second or 11.2 kilometer per second. Now, once the satellite is, it abandons itself from the gravitational field of Earth, at that moment, the satellite now will be considered in space. It is now considered in space, and now, in order to rotate the satellite around the Earth, it will require to have a velocity in order to remain in the orbit of Earth, which is known as orbital velocity. Now, why orbital velocity is important? Can't the satellite remain without any sort of, you know, sustainable speed? So it can, but we know that the gravitational force of attraction of Earth tends to act as a centripetal acceleration. It tends to act as a centripetal acceleration occurs due to the acceleration due to gravity, due to which it leads to centripetal force, which is in terms of gravitational force of attraction from the Earth, due to which this would be considered as the distance from which the centripetal force of attraction is, what do we call it, centripetal force of attraction is, acting towards it. Now, in order to remove within the centripetal force of attraction, there must be a force which is causing the satellite to move in its linear path, such that if there is, a centripetal force being applied over from the Earth, in terms of gravitational force of attraction towards the satellite to come downwards or towards the center of the Earth, there should also be a force applied, uh, which is in terms of tangential velocity. There should be a force applied which would be the centrifugal force, and that centrifugal force requires a sustained speed, in which the tangential velocity, a sustained speed or sustained velocity, which is known as a tangential velocity. That tangential velocity is necessary in order to maintain its orbit within the Earth, because within the Earth's orbit, because in order to revolve around the Earth, the centripetal force, it requires some velocity in order to abandon itself from the centripetal force. Formula for it includes very simple. We know that formula of centripetal force is equals to mv square upon r, and formula for, you know two a gravitational force of attraction between two bodies is equals to g m upon r square. Here g m1 m2, m will be capital M is considered as mass of Earth, small m is considered as the mass of satellite. When we are going to manipulate it, answer will be equal to radical gm upon r, where r is not only the radius of Earth, but also the radius of Earth plus the height at which the satellite is launched above the equator of Earth. So this is a point to ponder. Apart from that, uh, this is a basic observation. And one more thing, Kepler's third law. Kepler has presented three laws. Second law is known as law of conservation of angular momentum. Third law is known as the relationship between, it showcases the relationship between the orbital radius and of orbital radius as well as the orbital period of an orbit of a satellite revolving in an orbit. Let's see how. The statement says the square of the orbital period of a planet is proportional to the cube of the orbit's semi-major axis. We know that formula for period, we know the formula for velocity first and foremost is 2 pi r upon t. 2 pi r upon t. How did it come? We already know about it. We know that here, we know that here v is equals to r omega, right? And omega here is 2 pi upon t. So when we are going to multiply it, v is equals to 2 pi r upon t will be the answer, right? Now what we are going to do is to put the value of v. Value of v is radical gm upon r. So radical gm upon r is equals to 2 pi r upon t. Now what I'm going to do is to take square on both side. When I'm going to take the square on both side, it will be equal to gm upon r is equals to 4 pi square r square upon t square. And further, when I'm going to manipulate it, I'll get the final equation, which will be t square is equals to 4 pi square upon gm r cube. Here time period, it is measured in seconds, it is constant value. These all values are considered to be constant because pi is constant, 4 is constant, gravitational constant is constant, mass of earth is constant. So these are the constant values. And here the value of r cube is variable because we are because it is having the value of height of over which the satellite is launched as well as the radius of the earth. So this is a variable quantity. So after taking the constant aside and variable aside, this equation shows that the time period for the orbit is directly proportional to the radius of the orbit, which is represented by t square is directly proportional to r cube. This is the equation which is given by Kepler's third law. Now coming to some common observations in our daily life of centripetal force. We know that usually whenever there is centripetal force applying over a system, the centripetal force being applied over the system will tend to move the body in a circular path. So usually whenever we are having roads, whenever there is a curved pathway in a road, let's suppose this is a road going on and there is a sudden curved pathway a sudden curved pathway going on a highway, and we all know that at highway the cars are at a very high speed. So at that moment, as the car are at a very high speed, at that point this forms a circular motion, an angular motion, when the body is revolving in it, right? So in this case, as the body is revolving here, let's suppose this is a car. This car is moving through the circular pathway in a speed. So what we are having logically is, so there are more chances of that car to slide over or you know have an accident within that uh, curved path, because there's no sort of centripetal force in order to stop it. There's no particular type of centripetal force which can stop it in order to you know um, in order to direct it towards the center of that curve. So in order to direct it towards the center of that curve, there is a technique which is utilized by our governments, that we are having banked curves, such that this is a road. Let me just try to draw a simple structure. Let's suppose this is the road going on, and here by a side the roads are a bit curved. a bit curved, which means these are a bit steeped. A bit steeped. Let me draw it. uh, just trying to draw a rough diagram. So these are basically the you know uh, curved pathways. These curved pathways which are obtained over here are known as curved banks. These curved banks are utilized in order to increase the angle theta of the normal force which is being applied over the road, such that if there is a road, this is, let's suppose this is a road. If the road is a bit curved, it is a bit steeper, then it will be having the angle with the soil as theta. This would be the angle theta, and that would, let's suppose this is a car. This is a car, right? This is angle theta. This is car. Let me just try to draw a rough structure, right? So this is a rough structure of a car anyways. So this is a car and this is going on this steeper angle. So at that moment, the weight which would be weight of the car will be directed towards the downward side, right? While the normal force which would be created in reaction to the which would be applied by the road in reaction to the weight of the car will be equal to n, or the normal force. It is represented by n, which would be in the direction of, as road is applying according to the third law of motion, as the car is applying a force over the road will be applying a force over it in return. So this is the normal force applied by the road. Once the force is applied, we can name this force as normal force. Now what we need to do here is to consider its components. There are two components of its force. One is the x component, and second includes the y component. Oops. X component and y component. Let me just write it. It's x component, and that is equals to n cos theta. N cos theta. Second component is sine, vertical component, which is known as sine cos theta. Sine theta, sorry, sine theta and sine theta. Now here n cos theta is parallel to weight, which is mg. Now both cancel each other out. So whenever there is a banked curve, that banked curve, if there is an ideal bank curve which is having the theta ideal to the velocity of the car and radius of the curve, at that moment, that theta having ideality with the angle theta having the ideality with the velocity of the car and the radius of that curve will be written in terms of, you know ideal banking. Now what we are going to do is to derive a formula for ideal banking, such that whenever we are going through a road which is having the radius, let's suppose 2 meter, and does not support more than 140 kilometer per hour of speed, then that moment we are going to utilize under these conditions to find the angle between the curved banking, right? So this is only the one part. So n sine theta and cos theta would be there, as n sine theta and s cos theta would be there, and cos theta and w will be cancelled. Or in other words, we can also say that horizontal component of the force, this is basically the normal force. So normal force can be written in terms of and cos theta, which is equals to w, which is equals to mg. While on the other hand side, the vertical component and horizontal components being equal, when we are going to equate both of the components, because both are components of what, these are components of force, due to which n sine theta will be placed over here, and sine theta will be placed over here. Now here, what we actually need to do is to have the vertical components of vertical and horizontal components of weight as well, which means weight of the car as well. Vertical components of the weight of the car will be having mg cos theta and mg sin theta. Here mg cos theta will be equal to mg sin theta, while n cos theta and n sin n cos theta and mg sin theta will be cancelled each other out, and n cos theta and mg sin theta will be cancelled each other out, and mg cos theta will be equal to n sine theta. This is how we derive it, mg cos theta. Once we are done with it, that moment, m here, force is equals to what? Force is equals to, and the normal force is represented by mv square upon r, because this normal force vertical component acts as a centripetal force here. One more thing I forgot to tell, that here horizontal component cancels the horizontal component, but the vertical component of n sine theta, that n sine theta will be acting as a centripetal force, which will be directing the card towards the center of the curve, as a result of which it will be acting as a centripetal force. So this would be considered a centripetal force, due to which putting the value of n sine theta, which is mv square upon r sine theta, mv square upon r sine theta is equals to mg cos theta, mg cos theta. When we are going to manipulate it, m cancel with m, rest of the value will be in such a manner that here sine theta upon cos theta will be equal to tan theta. Tan theta is equals to v square upon rg. Now theta here is having tan multiplying with it. Inverse of theta, tan inverse will be inverse of tan inverse will go on the other hand side, due to which it will form theta is equals to tan inverse v square upon rg. This is the final equation, and this is the equation through which we can find the ideal angle which can be uh, adopted for the ideal velocity, the ideal angle which is associated with the velocity of the car, and the radius of the circle with respect to the angle which we are having. So in this case, if we are having a higher velocity of car, there will be higher value of angle. If there is less radius of car, radius of the curvature, there will be less value of theta. One more thing that I would like to highlight over here is that as there will be a dependency of theta on v and r, but there will be no dependency of theta on mass of the vehicle. It's a common MCQ. So this is only a brief intro, not an intro, but it's complete one shot of a topic. So this is all about today's video. Hopefully we'll meet again in another